Thank you for the steering committee for giving me the opportunity to give the presentation today. I'm Daniel Liang, working at CSIRO as a principal research scientist. The topic of my talk today is on shielding space radiation. First, I would like to acknowledge the contribution from colleagues and to the talk, and they include in my staff from CSIRO, also from the Australian National University and the RMIT. The talk including 4 parts. At the beginning, describe the challenges presented by space radiation, and secondly, explore the differences in the space radiation environment. Next is effort at CSIRO for developing the shielding material and fabrication technology. And finally, discuss and potential future shielding technology development. The damages by the radiation shielding is quite well documented. They can cause damaging to the human DNAs. They can decompose chemicals, including pharmaceutical products. They can malfunction, make the electronics not perform, including these inside medical devices. If there's no limitation on the size and the weight of the structure human can build in space, and should be able to build a very bulky structure to stop the radiation completely. But in reality, that's almost impossible to do. And this picture showing here is the structure of international space stations. You can see it's already quite bulky, consisting of aluminum alloy and polymer material. And they are the standard radiation shielding material these days. And even with this massive size, they are still not able to provide sufficient protection for the astronaut for prolonged durations. So challenges actually is going to develop lightweight material, small size, low cost, have multi-functions, which it can replace existing conventional shielding material. Now we talk about the different radiation environment. Depends where you are in the space, actually radiations and components are different. If you are at a place close to the Earth, radiation most like shaped by the global magnetic field of Earth. So you will have radiation confined by external, after and inner radiation belt surrounding Earth, and which is contain the particle from so-called solar particle events, SPEs, and galactic cosmic rays, GCRs, and the secondary radiation as well. So the majority of the particles radiation and at so-called LEO locations is low and medium proton energies, and also a large number of the electrons. If you reach the moon and also on the way to the Mars, and you wouldn't have a majority of the radiation influenced by the Earth magnetic field, and on the moon there's no magnetic field globally. So you really mainly encountered high energy galactic and cosmic rays, and the component radiation really is the high energy proton and heavy ions. So they're quite different from what you encounter and near Earth. If you and one of the people settlers within the space exhibitions and living in the colonies on Mars, radiation over there again is different again, because there's no global magnetic field and no atmosphere protecting Mars, and Mars surface bombarded constantly by the GCRS and CPES. So you have a quite significant background radiation from the radiation and surfaces. So you have almost high level of the radiation exposure on Mars in one day. It's the same as yours receive whole year round on Earth. Okay, now we'll talk about the effort normally we develop shielding material, the method and technologies. And tools most important for developing, selecting, and shielding material. One is modeling, and you use it to screening the large number of the material. Secondly, and you verify this selection, and based on the modeling, use ground analog radiation testing. And the picture showed here is one of the high energy proton radiation testing. And CSIRO conducted in the US to testing the high energy proton radiation effect with the material. And this is analog to the environment and on the moon and on travel to the Mars. That's another example of the radiation testing on the ground. This one is at the Australian National University, but configured to testing the lower media protein radiation environment. That's much more similar to what you encounter at the LEO locations. And in the previous last one, we identified couple and material candidates, which are different, and for LEO and for the high energy protein radiation and shielding effectiveness, and they are better than the conventional aluminum and polymer shielding material currently be used in the spacecraft, space stations. Once you identify the material, and actually most of the challenges to fabricate them into the shape and the size, which is you can use to build your spacecraft and habitats and space stations. I gave a couple of examples here. First one is you make it into a thin layered composite. Use the thermal sintering method. This method, you can have multiple different material in different lines. They play different functions. And in addition to their radiation effectiveness, they probably will encounter other situations require they have sufficient mechanical property and other thermal and electronic performance requirements. And these materials need to be have the comprehensive testing, and in addition to the radiation shielding properties, they need to have a minimum defect, and they need to have a distribution of the ingredients. And of course, in some situations, when people required and higher thermal conductivity, they need to be conductive. But sometimes people do not want the conductivity too high; they need to be non-conductive. So that's one, and you have not only one property to enhance the material, you need to monitor and control its other property as well. Using these types and thin layers composite actually most suitable to protect and electronic devices, including medical devices, by simply put add on to the electronic chips, or as enclosed partition between the electronic integrated circuits. Another example is so-called aluminum matrix composite, AMC. And rather than make the radiation shielding material completely independent parts, and this second approach example actually is to embed radiation shielding material into the existing structure panels, frames, and body structures. This picture you can see, and this is a transection of aluminum structure on the surface, and a 10 millimeter thick radiation shielding material are being implanted, added into the surface aluminum component. So in this case, you have a multifunction material, while you have the aluminum and base material perform the normal roles at structure and component. The surface being enhanced to stop the radiation, to minimize radiation, and to protect whatever behind it. In these situations, you actually achieve the goals, multiple function without increase too much weight. Another advantage of this second technology, actually, you achieve other functions which is not expected. For example, and with the radiation shielding material embedded the surface layer, they actually it provides additional heat resistance, impact resistant, wear resistant property. They're actually very important in the space environment because of the large change in the temperature, potential impact from debris, other one, and actually protecting your structures. Makes actually the aluminum almost as strong as the steel on the surface. That's what the photo on the right-hand side indicates. The use of this AMC material is quite a wide range of the products can be used for. For example, and in the image you can see, and on the right-hand top is an enclosure of electronic devices. You can use this material, and that's an example actually showing the ultrasound devices in the International Space Station. On the bottom on the right is the actually design of the Boeing space for the human habitat for Moon and Gateway. And this AMC material apparently can use for construction the walls of this habitat with enhanced radiation shielding and property. And the bottom left actually is concept design and Japanese lunar vehicles, and so apparently this AMC material can use for this vehicle as well, give the strength as well, give the radiation protection. Finally, and give a couple of examples what's happening in the future of radiation shielding technology. So far we have been talking, so add on the material structure, it's called passive technology. Apparently, that's the limit you can do with the passive radiation shielding technology. So currently, people active developing so-called active shielding technology, and that's one example is using the magnetic field locally generated and to create the area with and which radiation can be deflected from it. And on the right-hand side, it's a picture of the students working and supervision of MIT and CSIRO. They divide the magnetic configuration, and which is actually can get the radiation free zone in the center. And on the left-hand side image is NASA's many years at decades still ongoing. They create the whole radiation protection, additive shielding space, and for the whole spacecraft. Another example is go a step further, not only use the magnetic field, actually they use magnetic field to confine the plasma inside the magnetic field, so they have enhanced active radiation shielding than other technology. And it has been claimed, that's work done by NASA, they claim you can shielding between up to 30 and 50% of radiation and deflected from your protected area, which is quite extraordinary. I think that's under my talk. Thank you very much for your attention.